Okay, guys, so I decided that I'll just go through some of the topics on the module two, well, not module two, unit two, Chem broad topics for 2022. Okay, so the electrolysis of brine, that's what we're doing today. So the electrolysis of brine is done with the diaphragm cell. There could also be a mercury cell, but we're going to make a bit of comparison between both cells a bit later. But in a nutshell, this just has everything you need to know in a condensed, I guess, fashion. All right. So first and foremost, brine is concentrated aqueous sodium chloride. All right. So let's say we had a tiny cup or a little shot glass, maybe. And let's say we fill that with water, or not water. Let's do salt first. Regular old table salt. Let's see we put that much in it. And we put a bit of water in it, but not enough to dissolve the salt completely. No, you're going to have a very high concentration of sodium chloride within that. So concentrated aqueous solution of sodium chloride is brine. You have natural lakes like the Pitch Lake in Trinidad and Tobago, I believe. That's brine. That's a brine lake. And so basically, by going through the electrolysis process, brine produces three products. Brine produces chlorine in the gaseous form, hydrogen gas as well, and sodium hydroxide. Okay, so just remember that. Okay, so whenever we go through the process of electrolysis or the electrolysis of brine, we produce chlorine, hydrogen, and sodium hydroxide, which is simply NaOH, right? NaOH. Now, the cell, the diaphragm cell that is, it's divided into two compartments. It has a cathode compartment and it has an anode compartment, as you can see here. And the compartment is divided by this thin line here. It's the diaphragm, and the diaphragm is made of asbestos, or predominantly of asbestos. And the electrolyte, that would be the concentrated brine solution. And now remember, in order to do electrolysis, we need an anode and we need a cathode. In this process, the anode is made of titanium, or they are titanium rods, and the anode is a positive electrode, right? How I remember it, anions to anode, so AA, and cations to cathode, right? I'm gonna show you how this makes a bit of sense in a bit. So anions are negatively charged ions and cations are positively charged. And by the law of electrostatic attraction, trust me, you know this, like charges will repel each other. However, unlike charges will go towards each other or attract each other. Therefore, if anions are negatively charged, they'll go towards a positively charged cathode, anode, or electrode rather, which would be the anode. And if the cations are positively charged, they'll go towards the negatively charged electrode, which in this case would be the cathode. So remember, A to A and C to C, anions to anode, cations to cathode. Now, in the diaphragm cell, as I said, the anodes are titanium rods, the cathodes are steel grids, right? So, yeah. And as I said, the diaphragm separates the anode compartment from the cathode compartment, and the diaphragm is made predominantly of asbestos. So now we're going to go into looking at what happens in the anode compartment and what happens in the cathode compartment. Here, I have a little diagram that I've taken from the study guide, all right? But that's not important right now. Just know that the diagram is here and I'll be basically telling you what happens. So first I went with A, because we're going in alphabetical order. So at the anode, remember the anode is made with titanium rods. So when you consider the solution, brine solution, that is, we have NaCl, aqueous. And if it's aqueous, that means it is in water. Anything that's aqueous is dissolved in water, right? So that means the ions present would be Na plus ions, Cl minus ions. You also have H plus ions and OH minus ions because water self-ionizes. H plus and OH minus, right? Now, with that said, remember A to A, so anions to anode. Here, you'll have the anions, Cl minus and OH minus. Which one will go towards the anode? The Cl minus ions. And this is because we're using concentrated brine solution. So the concentration of Cl minus ions will outweigh the OH minus ions and thus go towards the anode. And how do you know what happens at the anode? Remember this little mnemonic, I guess. So think about, I want you to picture an ox, maybe an anorexic ox, and a red cat. So basically, at the cathode, as I said, a red cat, reduction happens at the cathode. And at the anode, you have oxidation. So there are two animals I want you to picture when we think about electrolysis, an ox and a red cat. An ox, anode, oxidation, and red cat, reduction, cathode. So basically, as I said, you're going to have the Cl minus ions going towards the anode to be oxidized, all right? And these Cl minus ions will be oxidized to Cl2 gas or chlorine gas, which will be pumped out at the top of the anode compartment. So here is the half equation that would basically represent the oxidation of the chloride ions. So here, chloride has an oxidation state, or the chloride ion has an oxidation state of -1. And here in the elementary or elemental state, it's 0. The oxidation state is 0. So -1 is actually less than 0. So you'll see an increase from -1 to 0, which means or represents oxidation. Okay, so I hope that was clear. So just a bit of recap. So you have Cl minus ions and you have OH minus ions, right? Those are both anions. However, these chloride ions or the Cl minus ions, those will get oxidized at the anode because they're in a way higher concentration than the OH minus ions. And so what you'll have is these chloride ions, they will be oxidized at the anode and pumped out as chlorine gas at the top of the anode compartment. Now, when we consider the reaction at the cathode, right, red cat, reduction will happen here. So let's consider the ions present. You have sodium ions, you have Cl minus ions, H plus ions, and OH minus ions. At the cathode, you will have the H plus ions being reduced to hydrogen gas, right? So basically, remember, here, if you look at the half equation, here hydrogen has a +1 charge, and then in the elementary state, it's 0. Now, +1 to 0, 0 is less than 1, so this represents a decrease in oxidation states. So that represents reduction. So if the oxidation state increases, that's oxidation, and if it decreases, then that's reduction. So it's all good here because we have the oxidation of chloride ions in the anode compartment. And now we have the reduction of H plus ions in the cathode compartment. So now we have our two products so far. We have chlorine gas, hydrogen gas, and now we're going to look at how the sodium hydroxide is formed. Okay. This has a bit to do with Le Chatelier's principle, but let's see what we're talking about first. If we consider the following equilibrium expression, remember earlier I told you that water self-ionizes the H plus and OH minus ions, right? So basically dissociates, for the lack of a better word, or breaks apart. So when the H plus ions are removed from the solution, because at the cathode, H plus ions are reduced to hydrogen gas and it's pumped out. So if you remove H plus ions from a system in dynamic equilibrium, Le Chatelier's principle states that anything or any disturbance to a system in dynamic equilibrium, the system will try to combat or do the opposite of whatever you've done to disturb it in order to restore balance or equilibrium. So to restore the comfort of this equation or this chemical reaction here, what will happen is the system will try to replace the H plus ions and that you have removed, right? So you'll have the equilibrium shifting to this side or to the right, favoring the forward reaction where more water molecules will dissociate to replace the H plus ions that you have removed. And in that case, you'll be adding to the OH minus ions that were already there. So just in case you didn't get that, let me just repeat for a bit, right? So remember, when we're dealing with what happens at the cathode, we said H plus ions are reduced, right? When the H plus ions are reduced, it turns into hydrogen gas. So it's no longer H plus ions, but rather hydrogen gas, and that's pumping out. So every time an H plus ion gets turned into hydrogen gas, it's removing H plus ions from the solution. And so the system will try to replace whatever H plus ions you are removing. And in that case, the equilibrium will shift to the right, favoring the forward direction. And what you'll find is, along with the H plus ions being created or being replaced by to replace the ones that you removed, you'll also have an increase in OH minus ion concentration. So when the OH minus ion concentration increases to just enough, the solution will have a mixture of sodium hydroxide. So you'll start having interactions between the OH minus ions and the sodium ions that are free in solution because of the concentrated brine solution. Remember that? Concentrated sodium chloride solution. Remember, that's brine, Na plus and Cl minus. Because sodium chloride is highly concentrated in the solution, you're going to have high concentrations of sodium ions and high concentrations of chloride ions. Remember, we got rid of these chloride ions when they were oxidized at the anode and pumped out at the top of the anode compartment as, you know it, chlorine gas, good going. And so if you have concentrated Na plus and a high concentration of OH minus, there will be some interaction between them. And so this will become a mixture of both sodium hydroxide solution and sodium chloride solution as well. And this will be pumped out at the bottom of the anode compartment, the cathode compartment, right here. Boom, chihuahua. And that's basically the process. So I hope that was clear. So remember earlier, I was telling you that we could also use a mercury cell for the same process, right? And basically what we'll be doing is doing a little comparison between both the mercury cell and the diaphragm cell, right? Okay, so basically the mercury cell, there has been some controversy. To me, though, I would go, if I had to choose, I would go with the diaphragm cell, because I would say that the pros would outweigh the cons, even though, you don't have anything that's ideal in this world or perfect in this world. So I wouldn't say, the diaphragm cell is perfect while the mercury cell has a lot of issues. But by going through the little differences between the two, I hope then you'll be able to basically talk a bit about like which one would be better efficiently, I guess, and for sustainability. So if you consider the mercury cell, the first point says that it's expensive to construct, while the diaphragm cell is way cheaper or much cheaper to construct. So here we have the diaphragm cell basically outweighing the mercury cell at this point for the first point here. So it's cheaper, so it's more cost effective. That is the diaphragm cell. The mercury cell works at 4.5 volts, while the diaphragm cell works at 3.8 volts. And to me, that doesn't seem like a major difference in voltage, because that's just the 4.5 minus 3.8. You know what? I'm not going to even try. I'll just use my calculator for now. That says 0.7 voltage difference. And to me, that's a relatively small number. And I say relatively because maybe 0.7 is not large to me. Well, it's kind of large. Yeah, it's large, but when considering like a 4.5 and 3.8, it's not that large. If we were considering like a 0.00007 and a 0.7, then that's a huge difference. I hope you understand. So like here, even though I would say it's not a huge difference, the 3.8 volts here is lower, so it's actually more energy efficient, the diaphragm cell. Now, mercury is highly toxic, and the diaphragm cell, they say don't use toxic mercury. However, asbestos is toxic to humans because it can cause many respiratory disorders such as emphysema and even lead to lung cancer. So I don't even, when it comes on to toxicity, I guess mercury would have more detrimental effects, right? So I guess mercury gets the upper hand here when they say there is no asbestos diaphragm, right? But mercury is still toxic. And the asbestos diaphragm needs to be renewed quite often. And the asbestos dust is toxic. I guess you can basically reduce the effects by changing the diaphragm quite often. Sodium hydroxide produced in the mercury cell is of a higher purity than the sodium hydroxide that would be produced by the diaphragm cell. However, the mercury cell does not need a high purity of brine to work, or the mercury cell needs a higher purity of brine to work, while the diaphragm cell does not require that high purity of brine in order to carry out the process. So again, now let's recap question for you. What is produced, or what are the three products of the electrolysis of brine? Hope you went through it. So you have chlorine gas, hydrogen gas, and sodium hydroxide. Nicely done. All right, another cell, I don't think I mentioned this, but you can use a Castner cell as well to carry out the electrolysis of brine. So yeah, I think that's it. Oh, what is the anode made of? Or what's the anode? So that's titanium, the titanium rods. What's the cathode made of? Come faster than that if you want to get me. It's the steel grids. Nicely done. What's the electrolyte used in the process? This easy. Soft matter, sodium chloride solution. Nice. All right. What is the diaphragm predominantly made of? Asbestos. Hope you got it before me. I don't think you were expecting that one, you know? Real wassy on it. All right, so I guess this would be it for the electrolysis of brine. Happy studying and all the best on your examinations, guys.